This section's title simply tells us the focus. We'll be analyzing the settings, hyperparameters, that control how kernel principal component analysis works. It's like looking under the hood of a machine to see what makes it tick. This sets the stage. I'm using KernelPCA, a technique that uses a mathematical trick, the kernel, to make linear methods work on nonlinear data. Think of it as cleverly reshaping the data to make it easier to analyze. We'll be exploring how changing the various settings affects the results. The gamma parameter in the RBF, radial basis function, kernel controls how wide or narrow the Gaussian curve is. A smaller gamma creates a wider curve, capturing broader trends in the data. A larger gamma makes a narrower curve, focusing on local details. Imagine it like this. A wide lens captures a whole landscape, a narrow one, a detailed close-up. This setting dictates how much I reduce the complexity of my data. N_components tells me how many principal components, the most important features representing the data, to keep after the transformation. Keeping more captures more information, but it increases the computational cost and can lead to overfitting. The model becomes too specific to the training data and doesn't generalize well. Think of it like summarizing a long book. A short summary misses details, but a long one might be cumbersome. This statement is incorrect. The kernel parameter specifies which type of kernel function, e.g., RBF, linear, poly, to use with KernelPCA. Even if I have chosen RBF, the kernel setting is still there. It's just that it's already set for me in this case. It's like choosing a type of wrench. Even if I'm using a specific one right now, the choice of wrench type is still relevant. If I set fit_inverse_transform to true I can try to rebuild my original data from the reduced representation. This is useful for understanding information loss. However, because of reduced dimensionality, the reconstructed data might not be perfect. Some details will be lost. Think of compressing a picture. When you decompress it, you might lose some quality. I'll explain the key hyperparameters in Sklearn's KernelPCA. Think of hyperparameters as the knobs you adjust to tune your model's performance. We're focusing on the ones relevant to the radial basis function, RBF, kernel, a specific type of kernel used in KernelPCA. This hyperparameter dictates how many principal components you keep after the dimensionality reduction. A higher value means you keep more information, potentially improving accuracy but also increasing computational complexity and the risk of overfitting. It's like choosing how many essential features to keep from your initial dataset. You want enough to capture the important patterns but not so many that you're fitting to noise. This is a Boolean, true, false, hyperparameter. Setting it to true lets you try to reconstruct your original data from the lower dimensional representation created by KernelPCA. However, keep in mind that because of the information loss inherent in dimensionality reduction, the reconstruction might not be perfect. It's like trying to put a puzzle back together after removing some pieces. You'll get a decent picture, but it might not be flawless. Gamma, denoted as gamma, is crucial for the RBF kernel. It controls the width of the Gaussian kernel function, influencing how sensitive your model is to local versus global patterns in your data. A small gamma creates a wide kernel, emphasizing global relationships, while a large gamma creates a narrow kernel, focusing on local relationships. Think of it like adjusting the zoom on a map. A wide kernel, small gamma, shows the entire landscape, while a narrow kernel, large gamma, focuses on a single location. This parameter specifies the type of kernel function you want to use in KernelPCA, e.g., linear, poly, RBF, sigmoid, cosine. The RBF kernel is chosen in this specific case, but it's still a crucial parameter because you could easily change to another kernel. It's like selecting the right tool for a job. Different kernels are better suited for different data structures and relationships. This section's title clearly tells us that we're diving into the settings, hyperparameters, that control how kernel principal component analysis, KPCA, works. KPCA is a fancy way to shrink the size of your data while keeping the important stuff. Think of it like summarizing a long novel into a concise plot summary. We're exploring the specific knobs and dials we can adjust to fine-tune KPCA's behavior. Let's get to it. I'll explain the gamma hyperparameter. Imagine you're drawing circles on a map. Gamma controls how big or small those circles are. A smaller gamma means bigger circles, so you're considering a wider area, looking at the big picture, the global relationships. A larger gamma means tiny circles, focusing only on nearby points, emphasizing local details. This affects how KPCA transforms your data into a new, hopefully simpler, representation. The n_components hyperparameter dictates how many dimensions you want to keep after KPCA does its magic. More components mean you keep more information from the original data but also more complexity and possibly overfitting, meaning the model learns the training data too well and won't generalize well to new data. It's like choosing how many chapters to keep from your summarized novel. The more you retain, the more detail but more bulk. Find the right balance. Setting fit_inverse_transform to true is like having an undo button. After KPCA simplifies your data, you can try to rebuild the original data. However, since you threw some information away during simplification, the reconstruction won't be exactly perfect. It'll be an approximation. I see you're interested in the hyperparameters of KernelPCA. These are the settings you tweak to control how the algorithm behaves. Think of them as the knobs and dials on a sophisticated machine. In this case, we have four important ones: gamma, n_components, kernel, and fit_inverse_transform. We'll explore each one individually. These are the specific hyperparameters for scikit-learn's KernelPCA. Let's break them down. Gamma influences the width of our kernel function, shaping how the model weighs nearby versus distant data points. n_components sets how many dimensions we want to keep after our dimensionality reduction. Kernel determines the mathematical function we use to calculate relationships between data points. Fit_inverse_transform lets us try to rebuild our original data from the simplified version, useful for evaluating information loss. This is the abbreviation of kernel principal component analysis, a fancy technique we use to cleverly reduce the dimensions of our data while trying to preserve the most important information. It involves using kernels to perform these calculations in a high-dimensional space without explicitly mapping to it, which would be computationally expensive. It's a powerful tool in machine learning. This sets the stage for the entire problem. We're using KernelPCA, a dimensionality reduction technique, and we need to understand the roles of its hyperparameters. The gamma hyperparameter within the RBF kernel directly controls the influence of each data point. A smaller gamma leads to a wider kernel, meaning each point's influence extends further, capturing broader trends. A larger gamma focuses the influence locally, picking up more detail but potentially missing the big picture. It's like adjusting the zoom level of a camera. This hyperparameter dictates how many principal components you want to keep after the dimensionality reduction. More components mean more information retained, but also higher computational cost and increased risk of overfitting, where your model matches the training data too closely and performs poorly on new, unseen data. Think of it as deciding how many details to keep from a complex picture when creating a simplified version. I disagree. The kernel parameter is important. Even though we're using the RBF, radial basis function, kernel in this specific problem, the kernel parameter still defines the type of kernel being used. It allows you to switch to different kernels such as linear, poly, etc. It's not irrelevant, it just happens to be set to RBF in this problem. This is a really useful option. Setting this to true gives you the ability to attempt to reconstruct your original data after applying dimensionality reduction. However, keep in mind that some information will inevitably be lost in the reduction process. Therefore, the reconstruction will likely not be perfectly identical to the original data. It is a helpful tool for assessing the level of information loss. This section clearly states the focus is on understanding how the different hyperparameters in kernel principal component analysis, KPCA, affect the model's behavior. KPCA is a dimensionality reduction technique that uses kernel methods to map data into a higher dimensional feature space, making nonlinear relationships more manageable. We will examine the hyperparameters individually to get a better grasp of their impact. This explains the role of GAMMA in the radial basis function, RBF, kernel, which is a common kernel in KPCA. I think of GAMMA as a tuning knob for controlling the width of the Gaussian function. A smaller GAMMA creates a wider, flatter Gaussian, meaning that data points further away will still influence each other strongly. This leads to a more global view of the data's structure. A larger GAMMA creates a narrower, more peaked Gaussian, making it sensitive to local relationships only. This has a direct impact on how the data is mapped to the higher dimensional space, affecting the model. Here, NCOMPONENTS is the number of principal components that the model keeps after the dimensionality reduction is completed. Essentially, it decides how many dimensions I'm keeping. Increasing NCOMPONENTS preserves more information, higher variance explained, but it increases computation and might overfit to the training data if the number gets too high. It's a balancing act between information retention and model complexity. This is a similar trade-off to that found in many machine learning models. The parameter FITINVERSETRANSFORM enables the reconstruction of the initial data from its lower dimensional form. However, it's important to note that some information is lost in the reduction process. Therefore, the reconstruction will not be perfect. This might be useful for interpretation or further analysis of the model's behavior after dimensionality reduction. If FITINVERSETRANSFORM is set to true, then the model will try to reconstruct the original data to help us to understand what happened to the data during the dimensionality reduction. I see gamma as the control knob for the width of the Gaussian curve in the radial basis function, RBF, kernel. A smaller gamma means a wider curve, considering more data points broadly. A larger gamma makes a narrower curve, focusing more on local details. Think of it like adjusting the zoom on a map. Smaller gamma equals wide view. Larger gamma equals zoomed-in view. This option lets you try to rebuild the original data from the reduced dataset. It's like trying to put a puzzle back together after removing some pieces. You might get close, but it might not be perfect. Whether you can effectively reconstruct depends on how much information was lost during the dimension reduction. The kernel defines the type of math used to find relationships in your data. RBF is one type, like a specific tool. This parameter is always relevant because it lets you choose the tool for the job, even if RBF is the default choice for this problem. This dictates how many dimensions you keep after the dimension reduction. It's like choosing how many colors to use when painting a picture. More colors, components, give more detail, but also more work and potential for messing it up, overfitting. Fewer colors, components, are simpler, but may lose some important details. This is the title of the problem. I'm exploring kernel principal component analysis, a dimensionality reduction technique, using the scikit-learn library in Python. This is the core question that I need to answer. I'll examine each statement about KernelPCA's hyperparameters and determine which ones are true. Statement A is true. The GAMMA hyperparameter in the radial basis function, RBF, kernel controls the width of the Gaussian kernel. A smaller GAMMA value creates a wider kernel, which tends to capture broader, more global patterns in the data. Conversely, a larger GAMMA creates a narrower kernel, focusing on local relationships. I think of it like this: a wide lens captures a larger area, while a narrow lens focuses on a smaller detail. Statement B is also true. The NCOMPONENTS hyperparameter sets how many principal components I want to keep after applying the transformation. Increasing NCOMPONENTS retains more information, resulting in better variance explanation, but it increases the computational cost and might cause overfitting. It's a balance. More components mean better representation but risk overcomplicating the model. Statement D is true. Setting FITINVERSETRANSFORM to true lets me try to reconstruct the original data from the reduced dimensionality representation. However, because information is lost during dimensionality reduction, the reconstruction won't be perfect. It's like trying to rebuild a puzzle after removing some pieces. You can get close, but it won't be identical to the original. Statement C is false. The kernel hyperparameter is important. It specifies the type of kernel to use. Even if I've chosen RBF, the parameter still exists and would be used if I selected a different kernel like linear, poly, or sigmoid. Ignoring this parameter isn't a good idea.